Hello and welcome. In this presentation, we'll briefly talk about the hydropower modeling behind the Pan-European Climate Database, or PECD 4.2. The hydropower conversion model consists of a statistical machine learning model based on ensemble learning called random forest regression model, where hundreds of independent decision trees learn patterns from predictors, namely temperature and precipitation, to reproduce the target variables or predictants, which are the energy data of hydropower generation or inflow. The final prediction is obtained by averaging the outputs of all the decision trees in the ensemble or forest. The temporal resolution is weekly. The spatial resolution is that of the pan-European zones onshore, which, as you can see from this map, correspond to country level for most countries, with a few exceptions. Now, given the size of the domain and the absence of detailed publicly available data for the individual hydropower plants, such as plant heads, installed technologies, and artificial regulations, the idea of employing a physical hydrological model was discarded. This approach was instead adopted for its adaptability to the available inputs and the reduced computational costs. Since this is a data-driven model, the importance of reliable energy input data is crucial. In the PECD 4.2, we address several hydropower technologies: reservoirs, run-of-river and pondage, and open-loop pump storage. The input data are hence time series of hydropower generation and stored energy into reservoirs. Where monthly resolution data are available, also install capacity time series are used to get rid of those changes in generation signal that are due to new installations, this way improving the training of the model. The sources of energy data are three. Some data come directly from the single transmission system operators, the TSOs. These are regarded as the most reliable in agreement with ENTSO-E. Publicly available data coming from the transparency platform are used where possible in absence of the former source of information. And finally, inflows from the previous PECD version, the 3.1, were used where no other source could. While the generation can be almost directly fed to the model, the inflows must first be estimated. Therefore, when enough data is available, the inflows are estimated through balance equations, taking into account both generation and stored energy time series. Otherwise, the PECD 3.1 inflows are taken as best guess and directly fed to the model. Depending on the input data, the model will then output several different technologies, as mentioned earlier, each with its own abbreviation. Coming now to the predictors, temperature and precipitation data are first aggregated and then lagged over time. This preprocessing step is very important. The two variables are average in case of temperature or cumulated in case of precipitation over multiple weeks. This to account for the history of the weather and climate conditions of each region. At this point, the model is trained on the ERA 5 reanalysis data and on the available energy data, and is validated using a leave 1 year out procedure. This means that the model is trained to predict or estimate 1 year at a time, in this case 2015, by training on all other available years. It is then tested on 2016 and on 2017, and so on. And the model parameters yielding the best results are memorized for each region and for each technology. The model, at this point, is trained on all years available, depending on the energy input data at hand. The longer the time series, of course, the better. Once the model is trained, it can be fed by different climate forcings, such as the complete ERA 5 dataset, or several CMIP6 models with different scenarios. In this last case, mind that the climate data will be first bias adjusted with respect to era 5. This way, we can reconstruct the historical series of generation or inflow, as well as estimate their future projections. The figure to the right shows an example of model output for France. Reconstructed and projected time series are plotted as annual aggregates for run-of-river inflows. In blue, you can see the era 5 driven output spanning from 1950 to near present, while with different colors to the right, you can see the output of the model driven by 6 different CMIP 6 models under 2 out of 4 considered scenarios. In this presentation, we've seen an overview of the hydropower statistical model. We've mentioned the different energy data used as input and learned how crucial it is to obtain a long and reliable time series of generation, stored energy, and installed capacity to train the model. We touched upon the climate data used and the importance of considering the recent history. And finally, we went through the different runs of the modeling chain. In brief, this was the hydropower conversion model behind the PECD 4.2. Thanks for listening.